So it's 5:30.
You can start.
Yeah, you will introduce the speaker.
Yeah. So it's my pleasure to introduce Professor Fernanda Botelho. Welcome, Professor Botelho, to our department. We are so grateful that you are giving this talk. So Professor Fernanda Botelho is a full professor at the Department of Math Sciences at University of Memphis. She is also the director of Math Science graduate program there. Professor Botelho did her PhD from University of California at Berkeley and her undergrad from Universidade de Porto in Portugal. Her research topics are mainly operator theory, but she also works in geometry of Banach spaces and dynamical systems. She has more than 80 research articles published. She has lectured all over the world and directed several doctoral students, and she has worked in many National Science Foundation projects regarding educating math instructors. So without further ado, I pass the baton to Professor Botelho. Welcome, Professor Botelho.
Thank you very much for the introduction. Thanks to Sudishna, Stefan, and the organizers for inviting me and giving me a second chance. And actually, from the first talk I have given here, a pseudo colloquium talk, I got several suggestions and feedback that have influenced some interesting changes. So let me start. Thank you very much. So the title of my talk is Contractive Projections and Lifting of Operators on Banach Spaces. Many of the results presented here are just a product of joint work with Monica, which is a graduate student, a doctoral student at the University of Memphis, and my friend Richard Fleming from Central Michigan University. So here the main property we have been studying is the so-called quotient lifting property, and actually that appeared or emerged from a suggestion by TSS RKMVERI. And here is the statement. We say that a pair of Banach spaces, X and J, a closed subspace of it, has the quotient lifting property if and only if for every Banach space Y and the bounded operator S from Y into the quotient X by J, there exists a bounded operator S tilde that I shall refer to it as the lift of equal norm, and such that this equality holds. So S tilde followed by pi, which is the quotient map, is equal to S. So a pictorial representation of this property is in this triangle. We have X, and you have the quotient space, X by J. I'm not sure if you see my cursor or not. Okay, and you have.
I can see. Yeah, we can see.
Okay.
Yes.
And you have the quotient map pi from X onto the quotient space. So for a Banach space Y, for every Banach space Y and a bounded operator S, there exists what I'll be calling the lift S tilde, this that represented by blue here in this triangle, such that the diagram commutes and this S tilde and S have the same norm. So a norm-preserving lift. So this could be traced to some older properties, and the first of which is the lifting property for Banach spaces due to Lindenstrauss and Zafriri. And here is the statement. Here is the property for the space Y. So a Banach space Y is said to have the lifting property if and only if for every bounded operator psi from X onto a Banach space W, and for every bounded operator S from Y into W, there exists S hat, lift, such that this diagram commutes. So S hat followed by psi is equal to S. So in their book, it has been shown that it was shown there that L1 is a Banach space that satisfies this condition. So that led us to consider some alternate lifting properties, largely inspired on this one. And the first of which is what we call, so our attention now is focused on the space on the right lower corner on the triangle. W has the alternate lifting property if and only if given Banach spaces X and Y, an operator psi from X onto W, and a bounded operator S from Y into W, there exists a lift, S tilde, such that this equation holds, or S tilde followed by psi is equal to S. But no norm preservation is assumed. The second property, very much inspired by the quotient lift property that I just presented right a few minutes ago, we have Y has the alternate quotient lifting property, if and only if, for every Banach space X, a closed subspace J, and the bounded operator S from Y into the quotient, there exists a lift, S tilde, such that this condition holds, S is equal pi, or S tilde followed by pi, the quotient map. So the spaces on the right side on the triangle now are conditional by a Banach space and a closed subspace of it. So the same representation as before, translating those conditions, is here. So we have now for the alternate lifting property is a property of the space W, such that the following condition holds for every Y and bounded operator S. And here we have a bounded operator that is surjective, psi. There is a lift, such that this diagram commutes. So interestingly enough, so for a W with this property, having this property is equivalent to say that W is isomorphic to an L1 space for some suitable index set gamma, and this gamma, the cardinality of gamma is equal to the density of W. So the alternate quotient lifting property is here translated in this diagram. So we have, it's for the Banach space W, and now such that for every X and J, a closed subspace of X. Here, the psi was a bounded surjective operator, now is just the quotient map. And the S tilde is lift that makes this diagram commutative. And again, for this Banach spaces with this property are those and only those that are isomorphic to an L1 space. So though the focus seems apparently to be different on a space on the left lower corner, now a space on the right lower corner, so end up giving as the same collection of Banach spaces up to an isomorphism. Here, just to translate or give an idea how these properties transfer to subspaces, we have here this result. W is a Banach space, and suppose W1 is a complemented subspace of W, meaning that it's the range of a bounded projection with on W. And if W has the alternate quotient lifting property, or also the alternate lifting property also holds for that, then W1 also satisfies the same property. And the proof is almost one line. Here is the sketch. So suppose X is a Banach space and J is a closed subspace. W1 is complementing W, so therefore there is a projection P from W onto W1. Then given S, a bounded operator from W1 into the quotient space, and since W has the alternate quotient lifting property, S composed with P, so P followed by S defines a bounded operator from W into the quotient has a lift. That's the condition set in the definition for alternate quotient lifting property. And that lift is such that makes this equation down here true. So if the lift followed by the quotient map is equal S composed with P. But then restricting this lift to W1, which is a subspace of W, gives us the lift of the original operator S. So from this here, that led, the corollary is every separable infinite-dimensional complemented subspace of a space with alternate quotient lifting property or alternate lifting property is isomorphic to L1. As we mentioned before, so it was isomorphic to an L1 of gamma. Gamma, the cardinality of gamma being the density of the original space. If you are saying that it's separable, that cardinality is countable, so we retrieve the little L1. So from here, and invoking a result by Sembranos, 1984, that reads as follows: let K be an infinite compact Hausdorff space, and E be an infinite dimensional Banach space, then the space of continuous functions from K into the E contains, this with the infinite norm, contains a complemented subspace isomorphic to C naught. So that tells us, because it has a subspace isomorphic to C naught, and that does not have the alternate quotient lifting property, so does not the space. So in particular, we can create examples. So if we have, for example, W, compact infinite Hausdorff space, 0, 1, and just take an infinite Banach space, E, so how about C of omega again, then this space does not satisfy the property. And this applies to both alternate quotient lifting property or the alternate lifting property. More, it is also shown in the same paper that C of K1 cross or Cartesian product with K2 being two infinite compact Hausdorff spaces do not satisfy the alternate quotient lifting property, because it was shown in the aforementioned paper that they contain a complemented copy of C naught. So that gives us a list of examples to the Banach spaces that don't satisfy these properties. Now I'm going to review a few definitions to be used later. So we have a Banach space X, and we have a closed subspace J. And we have the definition of metric projection onto X. So is a set valued function such that for every X in X, we associate the set of all elements in J that are at a closest distance to X. So the set of little j's in the subspace capital J, such that the distance from X to J is equal to the norm X minus J. So if it's possible that for some X's in X, this set is empty. So this leads to the following definitions. J is said to be proximal if and only if for every X in X, this set associated to X, described above, is non-empty. So we can say that then the metric projection is defined everywhere. So if we assume that when it gives us empty set, it's not well defined, or not that we are interested in that case. So for J proximal with the metric projection P sub J, capital J, sorry for the typo, a selection of P sub J is a function Q such that for every X selects a value from the set P sub J of X. So if this is a selection, it's a choice of values from the set associated to each X via the metric projection. So if that selection happens to be linear, then we say that the metric projection has a linear selection. The last definition in the list is J is said to be Chebyshev subspace of X if and only if for every x in X there exists a unique point in J such that this is true. So the distance from X to J is equal to the norm of X minus J. In other words, P sub J of X is a function, not set valued, but just the image is reduced to a singleton. All right, so now let's recap again the quotient lifting property that I said at the very beginning. So this concerns a pair of spaces, both X a Banach space and J a closed subspace of X. Then the pair XJ has the quotient lifting property, if and only if for every Banach space Y, and the bounded operator S from Y into the quotient, there exists a norm-preserving lift S tilde that makes this diagram commutative. So in other words, S tilde followed by pi is equal to S. Here are some necessary and sufficient conditions for this property to hold. X is a Banach space and J is a closed subspace. If Xj has the quotient lifting property, then J is proximal in X. If Xj has the quotient lifting property, then the metric projection has a linear selection and J is a complemented subspace of X. If Xj has the quotient lifting property, Xj has quotient lifting power if and only if J is the kernel of a contractive projection, and if J is a proximal subspace of X and P sub J has a linear selection, then the pair X comma J has the quotient lifting property. Just an example of a pair with this property. Just take two Hilbert space, one of which is a closed subspace of the other. Then the pair has this property, and that's easy to see because just take the orthogonal projection onto J, and that's a selection of, that's one, it's a metric projection, and it's linear. And here I have, a result by Singer that somehow got off the page, which it's in the book by Singer, 1970, which says that uses the proximality of subspaces of a Banach space to characterize reflexivity of the space. In other words, X is reflexive if and only if for every closed subspace J is proximal in X. So that immediately says that if we just take a non-reflexive Banach space and there should exist a closed subspace, that it's not proximal and therefore the pair cannot have the quotient lifting property. So there are plenty of examples of both situations, pairs with the quotient lifting property and pairs without it. Okay, so now from my last talk, Professor Rao asked the question, how about simultaneous proximality? So, so if X, so we know from what I wrote that if Xj has the quotient lifting property, then J is proximal in X. And to prove this, we just assume that it's not proximal. Suppose I have a closed subspace that it's not proximal in X. Then there should be an element in X that for which we cannot find any element in J at that closest distance. And using that element, we define the span of that element, and that's what we place on the slot Y on in the diagram before, on the lower left corner, and then define the usual of the natural S and show that that S does not have a norm preserving lift. So Professor Rao asked the question, is it possible that you can derive along the same lines stronger or property? So the so-called simultaneous proximality, and here is the definition. So X is a Banach space, J is a closed subspace of X. Then J is said to be simultaneously proximal in X if for every finite subset of X, A, there exists a point in J sub 0, such that we can, that gives us the simultaneous closest point to the collection of that collection that is finite, so the points in A. So let's see what that translates. The infimum J in J of the maximum over all the elements in A, which is a finite set, of norm A minus J, from A coming from A, capital A, and J from the subspace J, is equal to the maximum of a single, that maximum, that infimum is attained at a single point from the subspace J, labeled here with J sub 0. So instead, in the proximality, we're taking just singletons. So the capital A was a singleton. Now we allow finitely many points from the bigger space, capital X. So the question was, does quotient lifting property imply simultaneous proximality of J in X? So the answer is yes. And here is an outline of the proof, and this is for two simultaneous proximality. So in other words, I'm just taking two A's, capital A's, with 2 points. So if finitely many, so an inductive argument would apply. It seems that it works fine. So here is the outline. I'm taking capital A with 2 elements, and then define this new space, X direct sum with X, endowed with the infinite norm or max norm, and consider a subspace that I call diagonal of J, and that's a closed subspace consisting of all the pairs of the form J comma J. So I call it diagonal, and that's a closed subspace on this direct sum. And we define F1 from this Banach space into the quotient space X by J, and define the natural way. You take X comma Y plus D of J and associate X plus J, okay? And so because the pair XJ has the quotient lifting property, this function F, or this operator F1 has a norm preserving lift. Let's call it F1 tilde, that goes from this quotient space X plus X diagonal with quotient by the diagonal of J into a X, such that this condition holds and it's not preserves the norm. Similar approach applies to F2 by using the second coordinate instead of the first, and the same considerations apply. Then if we take the identity from this space into this quotient space, so we have back to itself, so the identity map has a norm preserving lift defined the following way: identity of X comma Y plus dj, the diagonal space determined or defined by J, is equal the lift of F1 comma the lift of F2 quotient in the quotient space with the dj, so plus d of J, or diagonal of J. I'm sorry, that's what I mean here, by diagonal of J. So from this fact, we can derive that this pair has the quotient lifting property, which implies that the diagonal of J, well, d of J or diagonal of J is the same thing, is proximal in this direct sum, so X infinite sum with X, which is equivalent to say that J is simultaneously proximal in X. So instead of having sets with, so if this is true for 2 elements, then for 3, it just, or 4 or n follows similarly. So we believe that it's true. So now an example. Let's look at the one sum of a Hilbert space with the real numbers, just a real Banach space. Deutsch in 1982 showed that if H has dimension 2 and J is a subspace of H, then the metric projection onto J has a linear selection, and therefore the pair has the quotient lifting property. However, if H has dimension greater than 2, we can easily find J's subspace of one-dimensional subspaces. So here is an example. We take U of norm 1 and a third, for example. Then we choose vectors in H, 2 of them. So that's the reason we need here dimension greater than 2 that are mutually orthogonal and also orthogonal to U. Then if we define this element in X, the closest element in J to it exists, is unique, and it's this one we have, U, comma, 1/3. And again, similarly, and this is just minimizing one-dimensional, one variable function, so it's a calc 1 problem. And P sub j of this new situation, new vector, is again equal to the same thing, 1/2 plus U, comma, 1/3. And but if we consider the sum of these two vectors, the metric projection of this element on J is 1 over square root of 2 U, comma, 1/3, which is not equal to the sum of the P sub j of the vectors above. So that tells us that P sub j, so this one-dimensional space J is, okay, so this is completely defined. There is a unique element that it's closest. However, P sub j is not linear. Okay, so this example could be extended further, and if we consider instead of just one sum, as I listed before, a P sum using the P norm, and P greater or equal than 1, less or equal than infinity, then the subspaces, proper subspaces of X are of one of these three forms, actually 1 and 2. The first one is a one-dimensional subspace spanned by a vector from H and a scalar from R, from the second space, that it's a positive number because we can always transfer it. If it's negative to U, it doesn't change the norm. And that's one possible subspace of X. And the other two types are J is H1, which is a closed subspace of H. So Hilbert, also with the Hilbert structure. So is a closed subspace of H1 of H and direct sum with R, or H1 direct sum with 0. So these are the three forms for a subspace of X, a Banach space of that type, and then import the norm that we have on X, one of these P norms. Then what happens is, if we take J of the second type, then it's a closed subspace of X sub P. If you represent this as X sub P indicating the norm, then the pair has the quotient lifting property. But there are examples of subspaces of dimension 1, such that the pair has the quotient lifting property. We can get examples from this second form. But other examples, those of the first form, don't have the quotient lifting property. But one-dimensional subspaces are one-complemented. So there are examples of complemented subspaces of X, such that the pair the pair does not define a pair with the quotient lifting property. Okay, so some results here. If P is a contractive projection on X, then the pair X comma kernel of P has the quotient lifting property. And this is just one line. If X is in X, then the norm of X minus this element here, X minus P of X, which is an element in the kernel, is equal to the norm of Px, which is also equal to the norm of Px minus K for every K in the kernel. But since P is contractive, this is less or equal than the norm of X minus K. So therefore, that tells us that this element, X minus P of X, is the closest element to X. And therefore, we have so P defines a linear selection into the kernel. Identity minus P defines a linear selection onto the image. I'm sorry. P defines a linear selection onto the kernel, and namely x minus px. So if P is bicontractive, then the pair x comma kernel of P and also x comma range of P have the quotient lifting property, and that follows straightforwardly from the first statement, because bicontractive projection are those that both are contractive and its complementary projection is also contractive. So the norm of identity minus P is also equal to 1, and then applying that result on the first one tells us that the x comma the kernel of identity minus P, which by the way is the range of P, it has the quotient lifting property. Examples of such, we have M projections, M projection, L projections, and of course I have to always list the bicircular and general bicircular projections bicontractive. And here, just to give you a review of generalized bicircular projections, we have the definition is due to Forstner, Ilishevich, and Lee, back 2007. And the projection P from a Banach space back to itself is a generalized bicircular projection if and only if P plus lambda, the complementary projection of P, that means identity minus P, is a linear isometry. This implies that that isometry must be surjective. And this holds for some length of modulus 1 that it's not 1. So Diana Ilishevich showed in 2010, actually characterized those projections for the setting, here should be X, not A, JB star triple. And that turns out to be P is a generalized bicircular projection if and only if either P is the average of identity with an isometric reflection or P is Hermitian. And so, as we saw, those projections, pairing the space with the kernel and the range, we have examples of pairs that satisfy the quotient lifting property. And here is one example. We have X to be C of continuous functions of -1, 1. And then if we consider the isometry, an isometric reflection that takes a function and associates the function composed with reflection, meaning it takes a t on the interval -1 to 1 back to minus t. Then this isometric reflection, and the P is an example of a generalized bicircular projection, and the range of it is the set of the space of all odd functions or even functions, and the kernel is the space of all odd functions. And those pairs listed here, X comma the space of all even functions, and also X comma the space of odd functions, both have the quotient lifting property. So in an email by Professor Rao, he said that if X is an L1 predual, or at least call our attention for L1 preduals that have very nice properties, then so if X is an L1 predual, it has no non-trivial L-summand subspaces. So L-summand subspaces are subspaces that are range of an L projection. And then L projection word also, the definition was given a couple of slides before. So X naught, and given an X naught, an extreme point of the unit ball of X, then the span of X naught is a semi-L summand. And here is the definition of semi-L summand below. If F is a closed subspace of X, F is a semi-L summand if and only if for every V in F and for every Y in F1, which is a subset of X defined below, we have this property, norm of V is equal norm of V minus Y plus norm of Y. And F sub 1 is the set of all Y's in X such that Y is 0, or F, which is the subspace and the consideration, intersection with the face determined by this unit vector is empty. So that being said, here I recall a result by Lima in 1977 that says the following. If J is a closed non-trivial subspace of an L1 pre-dual space X, and the dimension of X is greater than 2, then J is a semi-L summon if and only if J is the span of an extreme point of the unit ball of X. And J is a semi-L summon if and only if, for every X in X, there exists a unique Y in J. So in particular, this tells us that J is going to be Chebyshev, such that the norm of X minus Y is equal to the distance of X to J, and the norm of X is equal to norm of Y plus norm of X minus Y. These two conditions imply that the pair Xj does not have the quotient lifting property. So from this, it follows that if I take a compact Hausdorff space and J is a subspace of all constant functions on C of omega, and this basically, so if I have omega to be, so constant functions are extreme points. The space of all constant functions is spanned by an extreme point, constant function equal to 1. And so therefore the previous result applies because C of omega is L1 pre-dual. Then the pair C of omega comma J has the quotient lifting property if and only if the cardinality of omega is less or equal than 2. So the previous condition says that the result holds for cardinality greater than 2. So this follows immediately. Another result following from a different theorem by Lima is the following. If J is a real or complex Banach space, J star is isometric to an L1 space for some measure mu, if and only if, so J is an L1 pre-dual, if and only if for every Banach space X containing J, there exists a projection on the dual such that the range is the annihilator of J, and the norm of identity minus P is less or equal than 1. From this, it follows that if I take, if this setting from setting of the Lima's theorem, if I have that situation, in other words, given a Banach space that contains J, which is an L1 pre-dual space, then the pair, the dual space of X and the annihilator of J also has the quotient lifting property, because identity minus P is a contraction. Okay, so if another necessary condition for the pair Xj to have the quotient lifting property is that the quotient X by J is isometrically embedded in X. So the proof goes as follows. If X comma J has the quotient lifting property, then the identity operator on the quotient space has norm 1, has a norm 1 lift, so has a lift that preserves the norm. So I call it identity tilde from X, quotient X with J into X, such that this equality holds. So then, given an element in the quotient, label it X plus J, we have that the norm of X plus J is equal to this, because this composition is equal to the identity. So I can replace this with pi composed with the identity tilde, the lift of the identity at X plus J. Now, using the fact that pi is a quotient map, has norm less or equal than 1, then we have this inequality being true. And again, identity tilde is a norm-preserving lift of the identity, so has norm 1, so we have this condition. So therefore, all of these norms here are equal, and implies that identity tilde is an isometry. So, the quotient space is isometrically embedded into X. So if X, the quotient X with J is isometrically embedded in X via an isometry that it's right inverse of the quotient map, then the pair has also the quotient lifting property, because this embedding allows us to define the lift of a bounded operator. So the question came, so here is an example, because the question came up, is this always true? Can we always get this working? But if we look at this example, we already know that here is L3, so we have, we can look at this space as continuous functions from 3 points into the reals. And with the infinite norm, so that's what we have in the first slot. And here is a constant function, 1, 1, 1. So here is a one-dimensional subspace, and we already saw, because the cardinality of the domain is greater than 2, this is not going to have quotient lifting property. However, we can do it in a different way by noticing that the quotient space is isometrically isomorphic to a space of dimension 2, R squared, endowed with this norm. Okay, so let's see if I have more details here. So this isometrically isomorphism is easily seen that is given by x, y, z plus j assigns to this point in the quotient, x minus z over 2, y minus z over 2, and this is, though this is an element in R2, and the norm of this element, using this here, turns out to be an isometric embedding. And so what we have here is, if we consider S from y into x tilde, and such that even in this way, this S has norm 1, but any possible lift has norm greater than 1. But the point of this is, let's go here to the diagram that represents this. We have S as described above, and we have the quotient map, that this space here, x tilde, is R squared, endowed with that max norm of those 3 elements. And it's isometric, isomorphic to the quotient space. So it turns out that the space, the quotient space is isometrically embedded in X, because just consider phi of A, B, C plus J into A, B, A minus B. And this is an isometry, and it's in R3. And what we have here is isometrically isomorphic to R2, as we saw before. But this isometry, this is not a right inverse of the quotient map, and there is no right inverse of the quotient map that exists. There is no such right inverse, because if it would exist, then we have the quotient lifting holding. So this to us was, at least to me, was an interesting example to study, and because for some time I was wondering if this was always true. So if there is an embedding in this, if X quotient by J is isometrically embedded in X, is it true that we always have that embedding being a right inverse of the quotient map? So if so, another result that I have here is, if F for every closed subspace J, the pair X, J has the quotient lifting property, then X is isomorphic to a Hilbert space. And this follows because X, if for every J, this pair has the quotient lifting property, then J is complemented. And there is a result due to Lindenstrauss and Zafriri, 1971, that says this is sufficient to conclude that, that space X is isomorphic to a Hilbert space. Professor Sophie sent an email asking the question, is the condition X, J with the quotient lifting property for alpha J sufficient to conclude that X is isometric to a Hilbert space? It turns out that the example by Deutsch say this is not true. However, because this example is listed in a paper by Deutsch, and it's a Hilbert space on the first, say, coordinate, this R, infinite sum with R with the 2 norm, and then one sum with R. for every J subspace of this, as a closed subspace of this Banach space, the pair has the quotient lifting property, but the space is not isometric to a Hilbert space. However, it is true, it is an older result by James, 1947, that X being a Banach space with dimension at least 3, each closed subspace is Chebyshev and has a linear metric projection, if and only if X is isometric to a Hilbert space. So maybe the answer is no, but we may be very close to being true, the answer being yes. It turns out that this example here, Deutsche example, there are subspaces, and they are all dimension 1, as we saw from previous example I gave you, the X sub P spaces. They must be of dimension 1, such that they are not Chebyshev. Okay, so that's reason maybe that's so it's possible. I don't have the answer, but it's possible that if we enlarge one dimension, so if we have a Hilbert space with dimension 3, this is not possible anymore. I'm not sure. If you have the quotient, so now some consideration about this pair, L infinity, comma C naught. It's clear that this pair does not have the quotient lifting property. And so we had several approaches. Now we know more reasoning why, more reasons why this doesn't have a quotient lifting property. Maybe the easiest one is that C naught is not complemented in L infinity. But our first approach follow this plan using total sets that then was useful for the alternate quotient lifting property. So I'm going to just give you an outline of it. So first of all, C sub 0 is an M ideal. Then C sub 0 is proximal. And the M ideal, that's here the definition. So that means that the annihilator of C sub 0 is the range of an L projection in the dual space. Second point is that there is no injective bounded linear map from the quotient of L infinity by C sub 0 to L infinity. And the reason for that relies on a result by Arterburn and Whitley that says that the dual space of L infinity by C naught has no countable total set, no countable total subset. And this means, just to seeing the definition, tau sub alpha is a total subset of X star if and only if tau sub alpha, so this is a functional, collection of functionals, tau sub alpha of X z is equal to 0 for every alpha implies that z is 0. So L infinity is one such example. So there is a countable collection of functionals with this property. If there was an injective map, then we could define a countable total subset of this space, of this dual space of the quotient of L infinity by C naught. And we know that this doesn't exist. Then if we consider the identity on the quotient space and the quotient, on the quotient space, yes, L infinity by C naught, and the quotient map pi from L infinity to the L infinity over C naught. And if there would exist a lift of the identity, then it would be injective, which we know that that doesn't exist. So that's another alternative proof involving total existence of total subsets that also shows that the pair does not have the quotient lifting property. So what I was saying is that this pair also does not have the alternate lifting property. Using exactly the same approach, we conclude that if S is an identity map from L, this quotient space back to itself, and C be the quotient map from L infinity onto this quotient, if there exists S hat from L infinity quotient with C naught to L infinity, such that this equality holds, then S hat is an injective map, and we know that that doesn't exist. As a consequence of this, L infinity quotient by C naught is not isomorphic to an L1 space. Probably a well-known fact, but I just didn't know. So it was it followed from this study, that observation. So here, just how relating existence of linear selections with the quotient lifting property. Here, from a proximal linear subspace of a normed linear space X, we have defined here the metric complement of J, which is the set of all X in X such that the norm of X is equal to the distance from X to J. So we have here two results that are going to be useful for later observations. One of which is have a proximal subspace of a norm space X. P sub J has linear selection if and only if the metric complement contains a closed subspace that X is equal J plus J sub 1. The other observation is the metric complement due to Cheney and Ulbert is that the metric complement of J is closed, and also J is proximal if and only if X is equal J plus J sub 0. From here, we can conclude that J is being a proximal subspace of X, and J sub 0 is a subspace of X as well. Then X comma J has the quotient lifting property. This it just follows straightforwardly from the results before. So Cheney and Ulbert theorem states that X is equal J plus J naught. Since J sub 0 is a subspace, Deutsch theorem implies that P sub J has a linear selection, and therefore the pair has the quotient lifting property. So it's not true that for every the metric complement is always a subspace. And here is an easy example. Suppose you take L infinity and J is C sub 0. J sub 0 is not a subspace. Just considering X sub 1, 1, 1, 1, 1, 1, and X sub 2, 1, 1, minus 1, minus 1, etc. We have that both belong to the metric complement of C sub 0. However, the sum is a 2, 2, 0, 0, 0, which belongs to C sub 0, so does not belong to the metric complement. Okay, so the quotient lifting property and some considerations on the linearity of J sub 0. So does the quotient lifting property imply necessarily the linearity of the metric complement? And the answer is no. And because you see the pair, the example before, the pair L infinity C naught, we know that does not have the quotient lifting property. But it turns out that if we consider L2 of R plus R with infinity norm, and J is the non-trivial subspace of X, then J sub 0, which is metric complement, is a subspace if and only if J is generated by UV with the product not equal to 0, sorry. So this says that there are plenty of examples that where by the way, this space is such that every pair, the space X comma J has the quotient lifting property for every subspace. So it's easy to find subspaces with such that the metric complement is not a subspace. So, but the question remains: is this only the only example, or if we increase the dimension, is this true? Okay, so now, as we saw before, the quotient lifting property is equivalent to the existence of a linear selection. We have here the statement: X is a Banach space and J is a closed subspace. If it has the quotient lifting property, then the metric projection has a linear selection. Just to give you an outline of the proof of this. If we have the pair having the quotient lifting property, then there exists a lift of the identity on the quotient X by J, such that preserves the norm and makes this equality true. Then this composition pi followed by the lift of the identity, as you see, is an operator from x back to x, and it's a projection. And then we have that x can be written as a direct sum of the range and of the P with the kernel of P. And the kernel of P turns out to be J. And some one-line justification shows that the range of P is a subset of J sub 0. So therefore, Deutsch theorem implies that there exists P sub J has a linear selection, and therefore that's what we will, the result follows. Now, lastly, we have here a collection of spaces or pairs of spaces that have the linear selection, and therefore the pair satisfies the quotient lifting property. Here is, if we have X a Banach space and J is a proximal subspace of X, such that the metric projection P sub J has a linear selection, P going from X to J, then the pairs obtained from this also have the quotient lifting property and also have linear selection. This is LPX, LPJ for P greater or equal than 1, less or equal than infinity, C0x, C0j, space of continuous, sequence converging to 0. This is sequence converging. And C of X, C of J, C of omega compact Hausdorff space, comma X a Banach space, C of omega comma J, and L1 space and L1 subspace. The pair continuous function comma J with omega compact metrizable space and J an M ideal of C of omega has the quotient lifting property. And if X is reflexive and J is an M ideal on X, then the pair has the quotient lifting property as well. If X is not reflexive, Gem B and M ideal, we know that that's not true, like L infinity and C sub 0. Now, lastly, I have to say that, as I said at the beginning, we got some suggestions from some of which we got some answers, but others no. One of the interesting suggestions was to study this in a non-linear setting. We don't have much to add on that at this point, but surely is an interesting suggestion that was, I believe, by Sanchez, Egypt, and also TSS. And here are some references that were useful, very, very useful on this preparation. The first one is where most of these results are coming from. It's still a preprint, and it's joint work with Monica and Fleming. And lastly, I want to thank you very much for listening, and it has been a pleasure talking with you about this.
Let's thank the speaker for a very wonderful and engaging talk.
Thank you.
This was really, really very engaging, and so many new aspects than after what you said the last time. So many new things. So, any questions, anyone from the audience?
Wonderful talk.
Just wonderful.
Thank you.
I
don't know
everything is so clear.
Sorry?
Yes.
Here, somewhere? Oh.
The students just learn to answer questions. You know, if somebody asks questions, go home and work on them and answer next time you see them. That is a very good lesson.
Yeah. So, any questions, anyone?
I would just like to say, for matrix algebras, Rajendra Bhatia's student Priyanka Grover has many results regarding, you know, these proximal maps and things like that. And maybe students can see those works also, okay? Because this is mainly for encouraging students. And if they want to study finite dimensional case also, and study more Priyanka Grover's work and Bhatia's work, Tanvi Jain's work, but mainly Priyanka Grover, can give them more examples from finite dimensional spaces.
Okay. So, Ajit, I didn't quite follow everything you said. Could you please send me some information via email?
Okay, I'll send you, but the name is Priyanka Grover. Priyanka Grover.
Grover.
Grover, and she's Rajendra Bhatia's student. Okay.
Ajitji, if you are sending something to Fernanda, please also send it to me.
Yeah, I'll CC it to you so that you can tell students. But now there are more people, so I want the name to be registered. This is only to understand finite dimensional examples. And because things are so clear in finite dimensional setup, and most of the examples that Fernanda gave were from finite dimensional spaces even, isn't it?
Any other questions?
Thank you,
Ajitji. And any other comments, questions? If not, then I ask Stefan to maybe make some comments and conclude.
Okay. Yeah, so thank you very much for the wonderful and very clear talk. It was a pleasure to have you here. Next week there will not be any talk, but in 2 weeks, Sudeshna ma'am will talk about, we'll talk.
We'll talk. I don't know about what, but something, Yeah,
was very nice. See you again sometime.
Yes. Thank you again, Fernanda, for a wonderful, wonderful talk. And
thanks
everyone.
Thanks for all suggestions and comments I have received. So, as you see, help to understand this better, which is something I think it's a fascinating topic. And learn.
Thank you, Fernanda. Thank you, TSS. Thank you, Diana. Thank you, Ajitji, for being here. And we'll see all of you soon. Take care, everyone. Stay safe.
Have a good weekend.
Have a good weekend, everyone. Yes.
Bye.
Bye. Bye.
Okay. Bye-bye.
Okay, bye, everyone. Stay safe.